This question says, for the quadratic function f of x equals x squared plus 4x minus 12, answer the following parts. Does the graph f open up or down? So a quadratic function will be of the form f of x equals ax squared plus bx plus c. This is the general form of a quadratic, which is what we have. If you want to know whether a quadratic will open up meaning that the parabola is shaped like this, or opens down, meaning like this. If you want to know whether the parabola opens up or down, you're going to look at the value of a. So the value of a for our function is 1. So whenever a is positive, the graph will open up, and whenever a is negative, the graph will open down. So because Ra, the coefficient of the x squared term, is positive, our graph will open up. The next thing we want to focus on is what are the coordinates of the vertex. With a quadratic function that is in general form like this one is, we have two avenues to find the vertex. We can use a process called completing the square to manipulate that general form and put it into vertex form, and we can find the vertex that way, or we can use a vertex formula. So let's take a look at that. So if we were going to use completing the square, I would take my function f of x equals x squared plus 4x minus 12, and I would group the two x terms together and sort of write the minus 12 on the side. And we want to come up with what we might say is a magic number. This magic number is going to complete the square. It's going to make the expression factor into a perfect square, and then it will be in our vertex form. So what we do is we start with the coefficient of the x term. Well, let me back up a little bit. First, you want to make sure that you have a 1 in front of the x squared term. If you don't have a 1 already, you're going to factor out whatever that coefficient is. Since we have a coefficient of 1, we get to ignore that part and jump to this next part, where we take that number 4, we divide it by 2, and square it. 4 divided by 2 is 2, 2 squared is 4, so our magic number is 4. We're going to add that magic number here, but we need to balance our equation by also subtracting that amount over here. So now inside the parentheses, we have a quadratic expression that will factor to x and x, 2 and 2, the plus and a plus. We can combine those terms of minus 12 and minus 4 to become minus 16. And then we have x plus 2 squared minus 16. So we've taken that quadratic function in general form and now written it in vertex form. And the vertex form looks like this. F of x equals x minus h squared plus k, where hk is the vertex. So based on that, we can see what our h and k are. Our vertex is -2, -16. So we have the vertex, but I mentioned there was another way to find the vertex. You can use the vertex formula. And the vertex formula you can find the value of h, the x-coordinate of the vertex, by this formula, -b over 2a. So for our for our function, we already mentioned that a is 1, b is attached to the linear term, so b is 4, and c is our constant, which is negative 12. So for us, h is negative 4 over 2 times 1. That's negative 4 over 2, which is negative 2, just like we got over here. So we got the same x-coordinate. The way we get the y-coordinate, there is a formula for it, but I prefer just to take this x-coordinate and plug it into our function to get the y. So that would be negative 2 squared plus 4 times negative 2 minus 12. Negative 2 squared is a positive 4. 4 times negative 2 is negative 8. 4 minus 8 is negative 4. And negative 4 minus 12 is negative 16. So you can see we got the same y-coordinate of the vertex that we got with completing the square. So our vertex is negative 2, negative 16. The next part over here says, what is the equation of the axis of symmetry? So these parabolas have symmetry, and if we take a look at a sketch here, the symmetry happens when you pass through the vertex of that parabola. So you're going to have a symmetry, a mirror image on both sides of that vertex. And so we use a vertical line. So I've drawn a vertical line, that dashed line. And the equation of a vertical line is x equals. And since it passes through the vertex, we're going to use the x-coordinate of the vertex, h. So x equals negative 2 is the axis of symmetry for this example. In the next part, we want to find any x-intercepts. So to find x-intercepts, we let y equal 0, and f of x is the same thing as y. So I'm going to set my function equal to 0 and solve. This one can be solved, let's see if we can solve it by factoring. So 12 is 6 times 2, and we could use a positive 6 and a negative 2. Okay, so that's the correct factorization. We would set each factor equal to 0 using the zero product property. Get x equals negative 6 and x equals 2. So those are our x-intercepts. To find a y-intercept, that's the next part here. What is the y-intercept? We're going to let x equal 0. So let's calculate f of 0. 0 squared plus 4 times 0 minus 12 is negative 12. So negative 12 is our y-intercept. Next, I'm going to draw the graph. So we have now found that we have a vertex at negative 2, negative 16. And what I'm going to do is sort of adjust my picture just a little bit because I can see that my vertex is a little bit lower than I need it. So if I continue this down, that would be negative 13, 14, 15, 16. So negative 2, 16 is where the vertex would be. Then we have x-intercepts at negative 6 and positive 2. We have a y-intercept at negative 12. And we know we have a parabola that opens up. So right at this vertex here, I'm going to have a parabola that cups up or opens up. So this is a sketch of the graph. Now to find the domain of every quadratic will be negative infinity to infinity, or all real numbers. There are no restrictions on substituting into a quadratic function. However, the range, we notice, I'll use my ruler here, range are the y values if I go from bottom to top. The first time my ruler would hit the graph would be at the vertex, and then it would continue on to infinity. So in general, we're going to go from k to infinity for any up-facing parabola. For this example, our k is negative 16. So negative 16 to infinity, and with a bracket on that negative 16. Finally, we want to determine where the function is increasing and where it's decreasing. So if I trace this graph going from the left to right, I can see that the y values are decreasing along this section and then increasing along this section. So that section is marked off where the vertex is. So negative 2 is going to be kind of my mark where it changes. So I'm going to say that this function is decreasing from negative infinity to negative 2. And some definitions for increasing and decreasing will use a parenthesis here, and others will use a bracket. So just pay attention to the wording of the definition. What you're looking for is if it says open interval, you're going to use this way. Interval in general or closed interval would be the other way. For increasing, this graph or function would be increasing from negative 2 to infinity. And like I said before, you might need to use a bracket depending on the wording of the definition. Diana has available 440 yards of fencing and wishes to enclose a rectangular area. Express the area of the rectangle as a function of the width of the rectangle. For what value of W is the area the largest? What is the maximum area? So, since Diana wants to enclose a rectangular area, a rectangle has a length and a width, and the area of the rectangle can be calculated by length times width. Now, it seems like we're almost there, but we want to find the area as a function of width. Right now, we have area as a function of length and width. So what we need to do is we need to use this 440 yards to try to get rid of this variable of length in our function. So the 440 yards is the fencing, and the fencing will go around that rectangular region. And that fencing refers to the perimeter. So the perimeter of a rectangle is 2 times the length plus 2 times the width. So we're going to use all of that 440 yards of fencing. So I'll substitute 440 in for perimeter. And now I can solve this equation for the length so that I can get rid of that variable in the equation. So I'm going to solve for length by subtracting 2w on both sides. That gives me 2l equals 440 minus 2w. I'll divide both sides by 2, and that gives me a length of 220 minus w. So now we're going to be able to answer that part A. we said that the area of the rectangle is length times width, and now that I know that the length is 220 minus the width, I can substitute that in. And simplify a little bit, I've got 220w minus w squared. So now you can see that I have an area function whose only variable is w, which is width. So that is the answer to part A. And in part B, we want to find what value of w is the largest area. So this is kind of an optimization question, finding the largest in this case, but optimization is also finding the smallest in some cases. So what we know about this example is that our function a equals, I'm going to rearrange it a little bit, negative w squared plus 220w is a quadratic. And the graph of a quadratic is a parabola. This particular parabola has a negative leading coefficient, so it's going to be a down-facing parabola. So this is going to be the graph of the area function, a quadratic, and the highest area is going to occur at the vertex. So if we want to find the largest area, we need to find out what the value of that vertex is. We have a formula for calculating the vertex. We can find h by calculating negative b over 2a. That's negative 220 divided by 2 times negative 1. It's negative 220 divided by negative 2, and that's 110. Then we find the y part of the vertex by substituting that 110 into the area function. It's going to be negative 110 squared plus 220 times 110. Okay, so we're going to type that in our calculator. Negative 110 squared plus 220 times 110. And I get 12,100. Now just to pay attention, we've got two numbers here for the h and for the k. We want to make sure we know what those numbers mean. Typically in an ordered pair, hk, the h stands for the x and the k stands for the y. In our equation, we don't have x and y. We have a for the y part and w for the x part. So for the width, we get 110, that would be yards, and that is our h. And for the area, we get 12,100. That would be yards, square yards, and that's our k. So to answer the question, this is for part B and C, for what value of w is the area the largest? The area will be the largest when the width is 110 yards. And then for part C, what is the maximum area, or the largest area? The largest area will be 12,100 square yards. Solve the following inequality. X squared plus 3x is greater than 10. Now this particular inequality is a quadratic inequality because of the squared, and we have a process that we go through for solving these types of inequalities. The process starts with us treating this inequality instead like an equation. So I'm going to change that greater than symbol to an equal to, and move all the terms to the same side and solve. So I have x squared plus 3x minus 10. We can factor this into x and x. 5 times 2 is 10, a plus on the 5, a minus on the 2. I can set each factor equal to 0 using the zero product property and get x equals negative 5 and x equals 2. I'm going to take those values and put them on the number line. I'm going to mark them out in order, negative 5 and 2. Now since my inequality is a greater than, I'm going to mark those numbers on the number line with an open circle, because those values will make this expression equal to 0, and we're looking for it to be greater than 0. So we're actually going to rewrite this as well. X squared plus 3x minus 10 is greater than 0. So we're looking for when this expression is greater than 0, and these two values that we came up with make the expression equal 0. So we're not going to include them in our solution set. Well, now what we need to go do is test each one of these intervals to see which one of those intervals will make our inequality true. So I'll choose a test point in each interval. I can use a test point of -6 in the leftmost interval, a test point of 0 in the middle interval, and a test point of 3 in the right interval. So I'm going to take those test points of -6, 0, and 3, and we're going to substitute them into the expression x squared plus 3x minus 10. And what we're looking for is whether the expression comes out to be positive or negative, because positive or negative is going to tell us whether it's greater than 0 or less than 0. So let's test these values. So for -6, we get -6 squared plus 3 times -6 minus 10, and that's 36 minus 18 minus 10. 36 minus 18 is 18, and 18 minus 10 is 8. So what we found is that in this interval, the leftmost interval, our expression is positive. Let's continue with the next test point. We have a test point of 0, and in our expression, that's 0 squared plus 3 times 0 minus 10, which works out to be -10. So in the middle interval, our expression is negative. With our final test point, we have 3 squared plus 3 times 3 minus 10. That's 9 plus 9 minus 10. 18 minus 10 is 8. So in that leftmost interval, our expression is positive. So with our inequality, we want our expression to be greater than 0, and that would be our positive intervals here. So the intervals that make this inequality true are the leftmost interval from -infinity to -5. I used a parenthesis on the -5 to show that -5 is not included in the set. And then the rightmost interval is 2 to infinity. So the solution set for the inequality x squared plus 3x is greater than 10 is -infinity to -5 union with 2 to infinity. Use the graph shown to find the following: domain and range, intercepts, horizontal asymptotes, vertical asymptotes, oblique asymptotes. So let's start with the domain and range. What I like to do is to take my ruler and hold it vertically to find the domain. Now the reason I do this is because the domain is a set of x values for this function. And when I hold my ruler vertically, I'm pointing towards the x-axis. So you can see, I'll kind of mark here that my ruler is running across that x-axis as I go from left to right. So I start on the left because that's the smallest. And what I want to pay attention to is when my ruler is hitting the graph. Now this line right here, we're supposed to assume that it's going on forever. So my ruler is actually starting to hit the graph on -infinity. The domain starts at -infinity. And I'm continuing to hit the graph all the way up until I get to this vertical dashed line here. This piece of the graph over here continues on, getting closer and closer to that vertical dashed line, and that vertical dashed line is our vertical asymptote. Vertical asymptote is an undefined place for the graph, so I have a gap in my domain there, and that's occurring at 2. But if I notice on the other side of that vertical line, I have another piece of the graph down here where right when I cross over, my ruler will start touching that line immediately. So my domain picks up right after that asymptote and will continue on to infinity. We can do the same thing by holding our ruler horizontally, and now my ruler is pointing towards the y values, which is the range. We're going to start from bottom to top, that's smallest to largest, so our range starts at -infinity. It's going to continue. You can see on the right that it's getting closer and closer to that horizontal dashed line, and that horizontal dashed line is our horizontal asymptote. Based on this picture, we're going to take a break at that asymptote. So our y value is -3 there. And then immediately after that asymptote, you can see on the left here, the line is picking up again and goes to infinity. So our range is from -infinity to -3 and -3 to infinity. Then we're asked to find intercepts. We have 2 types of intercepts, X-intercepts and Y-intercepts. So an X-intercept is where the graph crosses the x-axis. So this line right here is the x-axis, and the graph is crossing the x-axis at this point right here, which is the origin. So we have an X-intercept at 0. And then we also have Y-intercepts, and a Y-intercept is where the graph crosses the y-axis. The y-axis is this vertical axis here, and the graph is crossing that vertical axis in the same spot at the origin. So we have a y-intercept also at 0. Then we're asked to find any horizontal asymptotes. So we already mentioned that this line right here is marking out the horizontal asymptote. But I don't want you to just rely on that dashed line being there. Let's really talk about what a horizontal asymptote is. A horizontal asymptote happens when your x is approaching infinity or negative infinity, and your y is approaching a specific number. So I can see on this piece of the graph, my x is going towards infinity, and my y is getting closer and closer and closer to this dashed line, and it's never going to reach it. And so my y is approaching -3. Over here on the other end of the graph, my x is approaching negative infinity, and my y is approaching that dashed line again, which is at -3. And so that's a definition of what a horizontal asymptote is. So when x is approaching infinity or negative infinity, and your y is approaching a specific number, in our case -3, you have a horizontal asymptote at that value, y equals -3. Not at that value, but along that line, y equals -3. So then I already mentioned earlier that we have a vertical asymptote that's happening right here. And I don't want you to rely on that dashed line. I want you to really understand what that definition means. So a vertical asymptote happens when your x is approaching some number and your y goes to infinity or negative infinity. So for this example, I'm looking at this piece of the graph right here, and my x is approaching the value of 2 from below 2, and my y is approaching infinity. And so that's following the definition of what a vertical asymptote is. If we also look on this piece of the graph, we can see that my x is approaching 2, this time from above, and the y is approaching negative infinity. So this is also following the definition of a vertical asymptote. So when that happens, we say that there is a vertical asymptote, and it occurs along the line x equals 2. And I got 2 from using that value that x is approaching here. And then finally, it's asking for oblique asymptotes. And for this example, we don't have any oblique asymptotes. An oblique asymptote would be if you had like a slanted line, and your graph would be approaching that line at infinity or negative infinity. Analyze the graph of the function r of x equals x squared over x squared minus x minus 2. So I'll go through each one of these parts. This is sort of a long process, so bear with me. First, we want to factor the numerator and denominator. So we have r of x. The numerator is already in factored form, but the denominator can be factored into x and x, 2 and 1, the minus on the 2 and the plus on the 1. This is helpful in finding the domain. So this is going to help us find out that the value of 2 and the value of -1 need to be excluded from the domain because they're going to cause a 0 in the denominator, and division by 0 is undefined. So our domain is x such that x is not 2 and x is not -1. Then we want to write our function in lowest terms. And since there are no common factors between the numerator and denominator, this function already is in lowest terms. Then we want to find any x-intercepts of the graph, x and y-intercepts. So let's find the y-intercept first. It's a little bit easier. So to find a y-intercept, you're going to let x be equal to 0. So we have r of 0 is 0 squared over 0 minus 2, 0 plus 1. And this ends up being 0 over negative 2 times 1, which is 0 over negative 2, and that's 0. So we have a y-intercept of 0, 0. So then we'll find the x-intercepts and also the behavior at those x-intercepts. So our function r of x equals x squared over x minus 2 times x plus 1. To find the x-intercept, we're going to let y equal 0. That's setting r of x equals 0. That's 0 equals x squared over x minus 2, x plus 1. We can solve this by multiplying both sides by x minus 2 times x plus 1. On the left, 0 times anything is 0. On the right, x minus 2 cancels, x plus 1 cancels, and I get x squared equals 0. And that gives me x equals 0. Now the behavior around that x-intercept we get from this multiplicity right here. So we have an x-intercept of 0 with multiplicity that is even. And so that means that at that x-intercept, the graph is going to touch the axis rather than cross the axis. So for that x-intercept, you would touch the axis. Then we want to find the vertical asymptote if one exists. And this is where it comes into play what we did earlier about writing the function in lowest terms. You want to make sure that you've canceled out any common factors before you try to determine the vertical asymptotes. We said that this function already was in lowest terms, so to find the vertical asymptotes, we would set those denominators equal to 0 and solve. And we have two vertical asymptotes for this function, a vertical asymptote at x equals 2 and a vertical asymptote at x equals negative 1. Now we want to determine the behavior of the graph on either side of the vertical asymptote. Now what we mean by that is we want to know if the y value is approaching infinity or negative infinity on either side of that vertical asymptote. Because the definition of a vertical asymptote says that x is going to approach that number and either the y will approach infinity or negative infinity. And we need to know what's happening. So I'm going to make a chart using my vertical asymptotes to help me decide what to do here. So I'm putting on my number line a negative 1, that's the location of one vertical asymptote, and a 2. I'm going to go ahead and put open circles on those values because I know that those are not included in the domain. So what I want to do is choose test points around that vertical asymptote and the other vertical asymptote and determining what's happening to the y value, and that's going to help me know whether it's going to negative infinity or positive infinity. So for my test point here, I'll choose negative 1.5. I'm trying to choose something that is close to negative 1, And on the other side, I'll choose negative 0.5. For the other vertical asymptote, I'll choose 2.5 and 1.5. And we're going to substitute those into our rational function, and we're looking for whether the y value comes out positive or negative. If it comes out positive, it's going to positive infinity. If it comes out negative, it's going to negative infinity. So my test points are negative 1.5, negative 0.5, 1.5, and 2.5. It might be helpful to do this with the calculator, but we're going to substitute into x squared over x minus 2 times x plus 1. You can certainly do this by hand, but I'll show you some features in the calculator that are helpful. So in my y equals menu, let me adjust this a little bit so you can see the whole thing. In my y equals menu, I will type my function. Let me do that in y1. X squared over, I'm going to put double parentheses, x minus 2 and x plus 1. And close that double parenthesis. Now then I'm going to go to the table. Now let's actually go to table set. So I hit second and window, which is table set. And what I want to do is I want my independent variable to be in ask mode. In ask mode, I'm going to be able to type which x values I want to plug in. So now I'll go to the table and type in the y values that I want. Negative 1.5, negative 0.5, 1.5, and 2.5. So remember, all I care about is the sign here, positive or negative. So for the first one, we got positive. The next one, we got negative. And then another negative and a positive. Okay, now let's go back to my chart. Now using the chart, what we found is that on this side it was positive, on this side it was negative. And then we have negative here and positive here. So what that tells me is that when I have my vertical asymptote, because it's positive on the left, the graph will be approaching infinity on the left. And because it's negative on the right of that asymptote at negative 1, my graph will be approaching negative infinity on that side. Same thing for the other vertical asymptote at 2. We got negative on the left and positive on the right. In the next part, we're going to try to determine the horizontal or oblique asymptote of our function. So to find the horizontal or oblique asymptotes, we need to follow this set of rules that have been summarized for us using calculus. So the rules use the degree of the numerator and the degree of the denominator, and it compares the degree of the numerator with the degree of denominator in these different cases. So for our example, our degree of the numerator, which I'll call n, is 2. And if we remember, this original expression had an x squared in it as well if we multiplied that out. So the degree of the denominator is 2 as well. So if we look at our cases, we have a case here where the degree of the numerator is equal to the degree of the denominator. So in that case, we're going to have a horizontal asymptote, and it's going to be the line y equals a sub n over b sub m. Now what that is the leading coefficient. And the leading coefficient are these coefficients that are attached to the highest degree term. So for our example, the highest degree term is this x squared, and we're going to have a coefficient of 1 here. And both of these have a coefficient of 1, and 1 times 1 is 1. So we have a leading coefficient, or our a sub n, for the numerator will be 1, and our b sub m, our leading coefficient for the denominator, will be 1 as well. So our horizontal asymptote is the line y equals 1. We just determined that we have a horizontal asymptote at y equals 0. And the next part we want to focus on is if the graph intersects that rational function. So we want to take a look and see if our graph will intersect that rational function. So the way we do that is we set the rational function x squared over x minus 2 times x plus 1 equal to our horizontal asymptote. This is going to tell us when they're equal to each other, when they overlap, when they intersect. So to solve this, I would multiply both sides by x minus 2 times x plus 1. This is going to allow me to clear the fractions. That cancels out these fractions from the left. And on the right, I'll multiply that out to get x squared plus x minus 2x minus 2. That's x squared equals x squared minus x minus 2. I can solve this equation by subtracting x squared on both sides. That gives me 0 equals negative x minus 2. And I can add x on both sides, and that gives me x equals negative 2. So for this example, the graph will intersect the horizontal asymptote at the value of x equals negative 2. That y value will be 1 for the horizontal asymptote. So the point where the graph crosses the horizontal asymptote will be the point negative 2, 1. So up to this point, we've gathered a lot of information that will be helpful for us to graph our rational function. We found that we have an x-intercept at 0, which is going to touch the axis instead of crossing it. We have a y-intercept at 0. We've got two vertical asymptotes at negative 1 and 2. We found a horizontal asymptote at y equals 1. We found that the graph will cross the horizontal asymptote at negative 2, 1. And we also have worked out what the end behavior will be around those vertical asymptotes. So that's very helpful. So let's see if we can come up with a sketch of the graph. So we have our X-intercept and Y-intercept at 0, 0. We have a vertical asymptote at negative 1. So I'm going to draw, let's use a different color. I'm going to use red. I'm going to draw a vertical asymptote at x equals negative 1. And another vertical asymptote at x equals 2. Sketching these lines out help you. It guides you how to draw the graph. We also have a horizontal asymptote at y equals 1. Let me bring that ruler back. Y equals 1, we have a horizontal asymptote. I'll draw a dashed horizontal line at y equals 1. And we have the point -2, 1. The point -2, 1 right here is where the graph crosses that horizontal asymptote. And then using my end behavior, I'll start at that point -2, 1, and I know I should be approaching the vertical asymptote going towards infinity on the left of -1, that vertical asymptote. On the other side, it'll come cross that asymptote and then start approaching the horizontal asymptote. Then on the other side with 0, 0, I'm going to be approaching -infinity on the right side of that asymptote and -infinity on the left side of the other asymptote. And then I don't have any points in this final section on the right, so I'd feel a little bit more comfortable if I picked one value, let's say an x of 3. So if I take an x value of 3 and substitute it into my function, r of 3 would be 3 squared over 3 minus 2 times 3 plus 1. It's 9 over 1 times 4. That's 9/4, which is about 2 point something, just a little bit more than 2. So at 3 and 2 point something, that would be about right here, I'm going to approach the vertical asymptote going to positive infinity and then approach the horizontal asymptote this way.